Welcome, everyone. It's my great pleasure to introduce our speaker today. My name is Rose Gottemuller. I'm the William J. Perry Lecturer here at the Stanford Center for International Security and Cooperation. And it gives me enormous pleasure to introduce Christopher Lawrence. He was a CSAC fellow back in 2014 to 16 approximately. That's right. Excellent. So I didn't have the pleasure of knowing him here, but I'm fascinated by his research. So Christopher Lawrence is currently the Assistant Professor of Science, Technology, and International Affairs at Georgetown University's Walsh School of Foreign Service. Also something I didn't know, Georgetown is my alma mater, but I didn't know they had this program going, and it's fantastic. So really looking forward, Chris, to your presentation today. So he studies the histories of U.S. nonproliferation engagement with North Korea and Iran, as well as the epistemic communities in the West that create knowledge about those countries' nuclear programs. His academic writing has been published in International Security, Social Studies of Science, Journal of Applied Physics, IEEE Transactions on Nuclear Science, and also in the more online publications such as Bulletin of the Atomic Scientists and War on the Rocks. So I'm absolutely delighted to have you here today, Chris, and we really look forward to your presentation. So over to you.
Great, thank you very much. It's great to be back at CSAC. The 2 years that I spent here were truly a milestone for me, and you'll probably detect some of the intellectual influences I got from some of the people I met while I was here. And actually, this is actually a newer project. This has nothing to do with Iran or North Korea. So I probably should have mentioned that in the bio that I sent. So this project, the core of this project is a Monte Carlo simulation of a hypothetical nuclear counterforce strike. But I'm using that simulation to illustrate a broader theory for how to think about nuclear arms racing and competition in the context of advanced, technologically complex nuclear weapon systems. So I think I'll spend maybe 10 minutes or so talking about the theory and articulating that, and then I'll talk about why I chose to model the systems I'm modeling, how I think that illustrates the theory, and then there'll be some results at the end. But I'm also really looking forward to some feedback because I want to get this ready for publication. So the contextual backdrop is, of course, China's recent expansion in its nuclear arsenal, and in particular, something like 300 new ICBM silos that are currently under construction, now visible in the satellite imagery. And these were discovered in the midst of ongoing debates in the West over whether the US should seek to retain nuclear primacy over China. So that's a policy that would likely entail an arms race. Or alternatively, should the US accept mutual vulnerability with its rising nuclear competitor, in some fear that that latter option might bring into question some of our extended deterrence commitments in East Asia. So in this context, political scientists and strategic analysts have been dusting off Cold War era quantitative methods to estimate the likely outcome of a counterforce strike. And they argue that the extremely high accuracy of modern US strategic missiles can seriously erode the retaliatory capabilities of US adversaries, and that we may be living in a new era of counterforce dominance in which states have to take seriously the possibility that their retaliatory nuclear forces might be eliminated in a disarming first strike. So several recent authors have used pretty straightforward calculations, and they purport to show that the US can expect to eliminate virtually all of the ICBM silos that it targets in a first strike with something like 95 to 98% confidence. Probably the most widely read example would be Lieber and Press's 2017 article titled A New Era of Counterforce. But since that article came out, several books and additional peer-reviewed articles have been published that use the same set of equations and arrive at the same prognosis. Now, the equations themselves date back to the MX debates during the 1970s. There's actually a 1973 paper by Davis and Schilling that published these, and so, you know, they've kind of come back into popularity. In my article, I refer to this set of equations as what I'm calling the standard linear model of counter-silo attack outcomes. And it's kind of the foil of my article, or the thing I'm arguing against. Because I believe that those equations embody kind of a techno-optimistic mindset that relies on a set of popular reductionist assumptions about modern technologies and how we can know and predict their behavior that I would argue are largely outdated. So for instance, it's often assumed that knowledge derived from component testing, testing the individual components within a system, can be unproblematically aggregated into holistic knowledge about the overall system performance. Similarly, it's often assumed that knowledge derived in system testing scenarios can be unproblematically translated into knowledge about system performance in real-world operational environments, and that a state's technological advancement and sophistication kind of automatically leads to more predictable and controllable weapon system performance. Again, I argue that these assumptions are outdated, and I point to a variety of now well-developed literatures across the natural, technical, and social sciences that warn against these reductionist assumptions. Things like chaos theory, study of complex systems, and from science and technology studies, the sociology of scientific testing. And these literatures have shown that in a variety of historical cases, aggregation of component testing into holistic system knowledge has actually been much more problematic than non-experts or policymakers might assume. That translation of system reliability in testing scenarios into operational predictions can also be problematic, and that technological advancement can sometimes increase uncertainty about system performance and behavior rather than decrease it. So I'm happy to talk in the Q&A about the different literatures I'm drawing from. It's kind of a diverse reading list, but I would say that they're generally united by a general warning against reductionist thinking. Now, it's important to keep in mind that it's not just any technologies that can defy prediction in the way these literatures suggest. So I can get in an airplane and expect to arrive at my destination. That's obviously a complex modern technology. So the question then becomes, is there a theory that can identify those technologies that might be harboring some of these unknown behaviors and surprises that we should be worried about? And to this day, probably the most widely or the most famous of these theories would be Charles Perrow's normal accidents theory. Now, some people in this room probably know Charles Perrow as the snowbird from Yale, which is how he used to introduce himself when he would come to the CSAC seminars. If you read nuclear stuff, you probably know him by way of Scott Sagan, who used normal accidents theory to analyze the possibility of accidental nuclear launches. Excuse me. So Charles Perrow focuses on the complexity of interactions between component parts inside a system. And he points out that when you combine large numbers of components into small packages, as we're often doing, there's this kind of combinatorial explosion that between the number of possible interaction pathways that can make it difficult or impossible to identify beforehand, in advance, all the possible intra-system interaction modes and failure modes that are possible. So he identifies two parameters, what he calls interactive complexity. So that's the presence of unknown, sometimes unfathomable interaction modes between component parts, and then tight coupling between component parts. So that's the sensitivity of those parts to the interactions. And he warns that when these two attributes are combined in technological systems whose failure would be catastrophic, then we should expect system failure to emerge from unforeseen mechanisms in the course of normal system operation. So that's why he calls it normal accidents, right? So it's not bad system design, it's not operator error. It's actually the holistic complexity of many modern systems that can give rise to what he would have called normal system failure. So this is his infamous interaction coupling chart where he's kind of qualitatively or intuitively plotting different technologies along these two dimensions. And it's for him, it's this upper right quadrant that he thinks we should be worried about. So for Perrow, the quintessential normal accident prone or normal failure prone system would be a civilian power reactor. Coming from a nuclear engineering department, I don't want to say whether I have a dog in that fight or whether I agree with him. Got some friends back at Michigan that might disagree with his analysis of that particular system, but I think he's clearly captured something about modern technologies. For Scott Sagan, it would have been the command and control infrastructures and the organizations that control our nuclear weapons. So what I'm doing in my article is I'm arguing that in the context of nuclear competition, ambitious nuclear doctrines that rely heavily on counterforce and damage limitation tend to push systems to migrate up into this upper right region where these unknown failure modes might be lurking. And it's not just unknown unknowns, it's also things like sensitive dependence to small variations in the input parameters, things like that. That's actually more what my model shows. I obviously can't tell you what the unknown unknowns are because we don't know them. But in my article, I identify several mechanisms that tend to push counterforce systems in this direction. And not only are retaliatory systems less sensitive to these mechanisms, they actually can benefit because they increase uncertainty. And in fact, the defender, for retaliatory missions, the defender can also do things to push the attacker's counterforce systems into this corner. And that's what we're going to see when we look at the Chinese silos and the spacing between those silos, which is the thing I'm simulating. I guess I should have defined counterforce. If people are not familiar with that term, that refers to a nuclear targeting that is targeting the other side's nuclear weapon systems. Damage limitation is another word for the same thing. Retaliatory systems or a mission would simply threaten a retaliation after a first strike. So I apologize if people were unfamiliar with that language. Let's see, I lost my train of thought there. Oh, okay, so with nuclear weapons counterforce systems, there's also an additional layer of uncertainty that Charles Perrault would not have even dealt with, because we obviously can't test these systems in a holistic way in any kind of realistic environment, operational environment. And I'm not just talking about single-shot nuclear tests in the desert or shooting a few missiles every year like we do. We're going to see that in a real counterforce strike, that's going to involve upwards of 600 high-yield nuclear weapons detonating in a relatively confined volume, and that's going to create an unprecedented physical environment. And I would argue that no amount of testing is going to tell us what we need to know about that environment to predict an outcome. So I bring these insights from STS and complexity theory into strategic debates about nuclear competition to argue that there's a balance of nuclear humility. So strategic thinkers often talk about the balance of resolve and the balance of capability. So the balance of resolve is in a nuclear crisis or a competition, which side cares more about the stakes of the crisis or the competition? Presumably their nuclear threats are more credible. Maybe that gives them an advantage. Others would talk about the balance of capability, which is pretty self-explanatory. Brinkmanship theorists have been arguing for decades which one of these matters more in determining the outcome of a crisis and giving one or the other side an advantage. I argue that nuclear competitions are also beset by a balance of nuclear humility. So states with more grandiose, technically demanding nuclear doctrines can be less confident in their technical knowledge, must work harder to retain their capabilities, and can hence be less certain in the success of their nuclear missions. More humble competitors, i.e. those merely threatening retaliation, can address their vulnerabilities with relatively modest, low-tech innovations and fret less over vagaries of the unknown. Crucially, the advantages and disadvantages of technological humility can run against those traditionally associated with the balances of capability and resolve. In other words, it's often the more technically capable states or the more desperate states, politically desperate states, that might feel more tempted to go down this road towards counterforce and damage limitation. Now, notice here I'm not just making an argument that counterforce is hard. I think everyone would agree that counterforce missions are more technically demanding than retaliatory missions. This is more an argument about the limits of technical knowledge and how technological complexity creates this kind of epistemic headwind that really doesn't burden retaliatory missions in the same way as it burdens counterforce missions. Presumably, somebody's going to have to hand the president a prediction of the likely outcomes of various nuclear options. And I'm arguing that counterforce and damage limitation draws states into really a labyrinth of compounding technological complexity that's ultimately going to make that prediction impossible. So to illustrate this, I stacked two competing nuclear weapon systems up against one another. So the United States Trident II D5 submarine-launched ballistic missile is widely considered perhaps the most advanced nuclear delivery system ever devised. It's the product of generations of research and development on the part of the world's most technologically advanced military power. It's extremely accurate. The most impressive numbers I've seen in the open source suggest that it might have a circular error probable or median miss distance of 90 meters. And in testing scenarios, it's performed quite reliably. So if we believe that the US Trident testing data is representative of what we can expect in a real nuclear strike, we might assign a reliability of 95% to the delivery vehicle. Now, the warhead has its own reliability that kind of rides up front of the calculation, but an exquisitely capable system. Facing this, China's silo-based ICBM force would appear to be the clear technological underdog. And I'm not arguing that China's holistically behind the US, whatever that would mean. But if we think of silo-based ICBMs, this is really decades-old Cold War era technology. So ICBMs themselves, the US and Soviet Union mastered ICBM technology in the late 50s, early 60s. We can probably assume that China has a relatively basic warhead design because I have a lot less nuclear test data than the US and Russia. Hardened silo basing similarly dates back to the early 60s, and even MIRV technology, multiple independent reentry vehicle technology, is essentially middle of the Cold War technology. Now, what's interesting about China's silos, and I think illustrates my theory, is that my analysis suggests that China may have chosen a clever geographical spacing that I think is going to really create problems for the Trident. So I'll talk about how that works in a minute. If we go back to the theory, the part of the theory where the more humble competitor, merely threatening retaliation, can do relatively low-tech, simple modifications to decades-old technology, geographical spacing would seem to me to be an example of this. Not take generations of research and development to draw dots on a map to decide where to bury these things. And if China can do that with a relatively old style of technology and really throw sand in the eyes of the much more advanced Trident, then that, I think, illustrates my theory. So I model this nuclear exchange using a Monte Carlo simulation. So if you're less familiar with Monte Carlo simulations, they essentially use random number generation to simulate complex physical phenomena. So the original application dates back to the Manhattan Project, where they used it to simulate neutron transport and other physical phenomena inside a nuclear weapon. But since that time, it's really become a bread and butter empirical method for a variety of mathematical and physical sciences. And in the context of strategic analysis, there's actually long been precedent for using Monte Carlo simulations to illustrate the complexity and uncertainty of a counterforce strike. So an example, a famous Steinbrunner and Garwin paper from 1976 did just this. So this was back during the MX debates, and people were using that simpler, what I'm calling the linear model that I'm critiquing, to say, oh my gosh, the Minuteman's going to be vulnerable. We got to build the MX missile. Steinbrunner and Garwin come along and say, not really. Turns out counterforce is much more complicated than those simpler models suggest, and they use a Monte Carlo simulation to illustrate that. So I'm drawing a lot from this Steinbrunner and Garwin paper. I'm also drawing a little bit from a Dick Garwin paper that came out that same year where he talks about kind of low-tech solutions to vulnerability. So I'm kind of drawing these older ideas and I'm trying to synthesize them into a broader theory, and I'm obviously updating things for modern systems. My analysis starts with a baseline scenario where I'm just drawing parameters from the open source literature. I call it the optimistic scenario because I'm not going to argue in a minute that the attacker can't really count on this level of performance in a real strike. But it's my baseline scenario that I'm starting with. So for the Trident, there are two warhead options for the Trident. So there's the high yield W88. So that's about 455 kilotons. I'm assuming 90 meters CEP, and then an overall system reliability of 90%. By the way, these are all numbers are all consistent with the Lieber and Press analysis. So I'm using all the same numbers that they use, but I'm just doing a more in-depth analysis. For China silos, I'm assuming 2000 PSI. That's the hardness rating. So that's a measure of the maximum peak overpressure that the silos can survive and still fire their missiles. There are some other mechanisms you can that I look at in the paper. So it turns out the duration of the pulse also matters, but this is a starting point. I'll also argue that China can probably do considerably better than this. They have major surpluses in a lot of the materials you need to harden silos. And then the diameter of the silos is consistent with China's DF41 and their DF31. So the DF41 is believed to have I've seen the DoD says 3 MIRVs. I've seen other people suggest that it could have 6, but I'm assuming 3. And there's also a variant of the DF31 that's believed to be MIRV capable. So these are my starting point assumptions. The second part of my analysis is I start tweaking these parameters by small amounts, and I have physical arguments for why these things are likely to be degraded for the attacker in the ways that I suggest. And then I look at the variation in the outcomes, and I'm measuring outcomes in terms of number of surviving warheads, Chinese warheads that could survive the strike, that China would have available to retaliate in a second strike. This is the figure at the end of my paper. I'll come back to this as kind of the punchline of my talk, and I'll say a few things more about how the figure is constructed. So if we go back to the FOIL, the article, the standard linear model that I'm critiquing, what does that suggest about this particular strike? So if we go to the Lieber and Press article, this table is drawn from there. Now this is before the Chinese silos came out, so they're imagining 200 targeted silos. I can just renormalize that number to 320, which is the number of Chinese silos that are under construction. If I do that, so this is what the standard linear model with the same parameters suggests for the Trident. For the higher yield, suggests basically no surviving silos with like 95 to 98% confidence. For the lower yield, W76, you might have 1.5 surviving silos, according to the standard linear model that Lieber and Press used. So that's a very impressive, optimistic result for the attacker. If the attacker believes this, they might see escalation as an attractive way out of a variety of plausible nuclear crises. A few things about the assumptions that are built into the standard linear model. So Lieber and Press assume 2-on-1 targeting. So this means that the attacker would devote 2 nuclear warheads to each silo that they're targeting to increase the chances of getting them all. This makes some implicit assumptions about the nuclear effects, as well as the precision with which the attacker can land the nuclear weapons in time. We call this time on target precision. So to think through this, let's imagine 2 consecutive detonations over the same targeted silo, and maybe T = 0 is at the first detonation. So for about the first 3.5 seconds, the silo would be shielded from the prompt nuclear effects, basically the fireball. The prompt nuclear radiations would also play a role, but after about 4 seconds, maybe, I'm going to emphasize maybe, the fireball rises enough to make way for the second shot. But then after about 7 or 8 seconds, the upward draft that it creates draws dirt and debris into the stem of the mushroom cloud as it's forming. It's expected that that would also be lethal to incoming reentry vehicles. The reason for that is that the reentry vehicles would be coming in hypersonic, so they're going about 2,000 meters per second when they reach their targets. At those speeds, even small particles of dust would be lethal to a reentry vehicle or to the warhead in a collision, either from the sheer momentum transfer or by penetrating the reentry vehicle. So maybe there's a window in time, I'll call it the second shot window, where the attacker, if they have sufficient time on target precision, can land the second shot. we'll see in a minute that the existence of this window is speculative, but it's one of the assumptions that's built into the Lieber and Press calculation. The other assumption is that the attacker can do what's known as reprogramming, and actually Trident, I believe, can do this. So if we imagine that the first 2-on-1 wave attack has subsided, and maybe the attacker can receive a signal from its missiles telling the attacker which missiles failed in the boost phase, and a lot of the failure modes are expected to be in the boost phase, then they can reprogram their remaining missiles to target the silos that they believe survived. So these are both important assumptions in the Lieber and Press model. So what does a Monte Carlo simulation allow me to simulate that isn't captured in the standard linear model? So the obvious thing is actually the dimension of time. It turns out the sequence of the attack is really important, so that's not captured in the standard linear model. And the other thing is the nuclear effects. And in my analysis, the really consequential one would be the dust cloud. So I'm following Steinbrunner and Garwin, and I do a simple momentum transfer calculation to estimate a minimum lethal particle size, and I get something like 2 grams as the minimum size of a particle that would be lethal to a reentry vehicle. Then I have some expressions that estimate the distribution over particle sizes and the density of particles in various parts of a nuclear dust cloud. And then I calculate a mean free path for the reentry vehicle inside the various parts of the mushroom cloud, and I implement that in my simulation. So why am I talking about the spacing? Well, if we compare to the American or Russian silos, those are about 5 to 6 kilometers separation between nearest neighbors. At those distances, a lot of these nuclear effects diminish and are less important for the attacker. Not all of them, but some of them. China's silos are much closer. They range between 2 and 2.5 kilometers separation between nearest neighbors. At those distances, a lot of the nuclear effects are likely to be more important for the attacker. Now, a little bit of a historical aside, if people remember some of the basing schemes that were proposed for the MX missile, one of them was called dense pack. That was actually a lot closer than this. It was actually hundreds of meters between silos. And the idea was that the nuclear effects could shield the silos to reduce their vulnerability. The problem with dense pack is that somebody was able to show that they were too close. And they enabled the attacker to do what's known as a pin-down attack. So a pin-down attack would be when you detonate nuclear weapons in space, you're basically filling a volume of space where the outgoing ICBM tracks would be traveling through with nuclear effects, and it's a matter of how many nuclear weapons you have to detonate per unit time, right? When the silos are really close together, it compresses those trajectories in space and makes it practical to do a pin-down attack. It seems to me that China may have picked a happy medium. So these are close enough to bring nuclear effects back into play, but not close enough to make it practical for the attacker to do a pin-down attack. So if we think about the basic features of a generic nuclear dust cloud, so we've got the head of the mushroom cloud. I'm actually not even simulating that. I think it's probably going to make things worse for the attacker, but we'll see they're probably already bad enough without it. Then you've got the stem, and then what's known as the sweep-up dust pedestal. So starting with the stem, again, following Steinbrunner and Garwin, what they do is they look at photographic data that's reported in Gladstone and Dolan, which is the famous nuclear weapons effects textbook. They fit a curve to that data to write down an expression for the relationship between the radius of the stem and the yield. So I've repeated that for the modern W88 system. That's a typo there. It should say yield of 455 kilotons. So in this figure, this is looking down on the human ICBM silo field in China. Each dot is a targeted silo, and the circles are the outlines of the projected stems of the nuclear dust clouds. So I think you can see from this figure that this probably takes reprogramming off the table. Because immediately after the first wave of attack, the entire silo field is going to be engulfed in essentially a solid volume of dust that's believed to be impenetrable by the incoming reentry vehicles, yet penetrable by ICBMs that would be just entering their boost phase if China launched them in retaliation. Estimates for how long the dust remains aloft are range from 1 to 2 hours. There are complex airflow fields in this region that are expected to keep some of the dust aloft. One clarification or caveat is that it should be seen as a very rough estimate, and the nuclear weapons effects literature emphasizes that the actual data from photographic data from Nevada test site has about a factor of 3 scatter in the data itself. So this would be a rough estimate. But you can see that they're considerably overlapped. They could be much narrower, and they'd still be a problem for the attacker. And then again, there would be a complex airflow field that would be mixing things in an unpredictable way. The attacker is not going to want to rely on reprogramming. So moving on to the dust pedestal, you might look at a photo of a nuclear dust cloud and think this is inconsequential. Turns out, behind the blast wave, there's another complex airflow field that, through a variety of mechanisms, has been observed to lost upwards of 10 centimeters of Earth, hundreds of meters into the air. So probably the most credible literature I saw on this was by Harold Broad, who's one of the famous nuclear weapons effects scientists, suggests that this might have a height of 400 meters. The radial extent corresponds to basically a threshold and peak overpressure from the blast wave between about 5 and 10 psi. And using scaling laws, that corresponds to about 2.5 to close to 4 kilometers. So these are likely going to engulf neighboring silos for the W-88. Now, another thing to keep in mind here is the attacker is going to want to assume the upper bound, not just because they're being cautious, but if you look at the pattern of the silo layout, then you'll see that in a rollback attack, which is the pattern that the attacker would probably use, each silo would have 2 or 3 intersecting blast waves going over it. And the literature emphasizes that not only do we not know, we don't know what happens when multiple blast waves intersect, we expect it to be greater than additive. In other words, the dust raised from or lofted from 3 nuclear blast waves intersecting each other is expected to be greater than 3 times the dust in height, density, and radial extent. Well, not radial extent, that would be a different relationship. Greater than 3 times what you'd expect from a single blast wave. So the attacker should expect probably the upper bound and maybe beyond. I calculated a mean free path for the reentry vehicle. So the reentry vehicles are also coming in a steep angle. So they're going to, I calculated, I think, 90 meters of a mean free path. The reentry vehicles are going to travel 2 or 3 of mean free paths before reaching their target. They're going to be vulnerable to that dust cloud, probably. So if we compare to the Lieber and Press result, the standard linear result, remember they say no surviving silos. My baseline scenario suggests for the high yield Trident W-88, 26 surviving silos on average. So if China's MIRVing, that's close to 80 high yield nuclear weapons that China would have available to retaliate with. Interestingly, in this baseline scenario, the W-76, the lower yield one, performs better. Does anybody have a guess as to why that would be? I'm used to teaching students. Sorry, I'm supposed to, where I have to get them to talk. So I'm assuming in my baseline scenario that the dust pedestal is not wide enough to engulf neighboring silos for the lower yield weapon. So that's why the lower yield Trident seems to outperform. I think the attacker would not want to count on that either because of this greater than additive combination of blast waves. But that's what I'm doing in my baseline result. But in any case, you've got close to 45 high yield nuclear weapons that China would have to retaliate with. The next part of my analysis, again, I'm sort of tweaking various parameters by small amounts to see what difference they make. That's illustrated in this table, but I'll step through this figure and kind of construct this figure. So basically, the way this is constructed is the vertical axis here corresponds to equivalent megatons that would potentially survive the first wave of attack that the defender, China, would have to retaliate with. And each column here corresponds to a different scenario. So here's my baseline scenario. The dark band is, so if you may know this, but in a Monte Carlo simulation, you simulate the whole thing millions of times. So in this scenario, the dark band is 65% of simulated cases. The lighter band is 95%. Now, the reason I've constructed this way has to do with the literature, the strategic literature. It turns out there are different theories for what the US might gain from having counterforce and damage limitation capability. So in the Lieber and Press, they define nuclear primacy as the ability to basically shield ourselves from damage and cost so we can basically escalate with impunity. So you would think of like what's an acceptable level of damage, probably for a US president, that's going to be very low, right? Even a single one of these warheads would be like dozens of 9/11s. So our baseline scenario is way above that. However, some people argue that, okay, maybe we can't get them all, but some is better than none. So they define what they call a range of meaningful damage limitation. So that's where I'm drawing from a paper by Charles Glazier and Steve Fetter, where they define a range of meaningful damage limitation extending up to something like 40 megatons. So that's why I've kind of done this vertical axis in megatons. So the first scenario, the first tweak to my baseline scenario is as I ask, okay, what if there's no second shot window? Turns out this existence of the second shot window is merely a matter of speculation. And in fact, Harold Broad made some arguments about the variation in how fast the fireball would rise that suggests that it probably doesn't exist or the attacker wouldn't want to count on it. We also wouldn't know the bounds of the window. So let's say if the second shot window doesn't exist, now the W76 has completely lost its advantage. It doesn't affect the W88 as much because it's sufficiently high yield, and maybe at 90 meters, if we believe that, then it's sufficiently accurate that it doesn't necessarily need the second shot. But for the W76, it needs the second shot. So it really hurts the W76 performance. Now, each one of these, I'm kind of reverting to my baseline scenario and only adjusting this parameter. The next thing I do is what's called fat-tailed distributions of the reentry vehicle dispersion. So reentry vehicle dispersion is the miss distance, basically. So if you imagine shooting 1,000 missiles at the same target, you'd get a distribution. It's assumed in the standard linear model that the distribution is a two-dimensional Gaussian. The width of the distribution, so this is the standard linear model calculation for single shot kill probability. The way they derive this is the width of the Gaussians is determined by the CEP, and then the lethal radius, you integrate out to the lethal radius to get your single shot kill probability. We don't know if the distribution is Gaussian. We also do know that it's very likely to be offset from the center by the systematic error, which we can't really know because we'd be shooting over a novel trajectory. And it doesn't have to shift enough to get the whole distribution out. It just has to shift enough so that this integral doesn't work anymore because you'd be integrating different part of the distribution. So there's a variety of things that could be going on here that would violate this assumption. The one I look at in the article is just a fat tail distribution. So this dotted line is basically bell curve Gaussian distribution, and the fat-tailed one is a kind of a cartoon. It's exaggerated fat-tailed distribution. And you can see where the two cross, where they cross in relation to the lethal radius could pretty substantially change the single shot kill probability. Now, what's interesting here is two things. One, the practitioners probably can't measure this because even if they do a bunch of tests, most of the data, even in the fat-tailed distributions, clustered around the center. So it would require an inordinate amount of testing to determine that it's a fat tail distribution and determine by how much. Also, it's more likely to be a fat tail distribution the more advanced the weapon system gets. So in the old days, you would have had maybe a dozen or so terms in the error budget. You'd be adding those in quadrature, but it's believed that as the US enhanced its accuracy over many years, they chipped away at those terms of the error budget differentially, leaving probably an error budget that's dominated by a few terms. And those terms are likely to be non-Gaussian. Things like the weather and asymmetric ablation of the reentry vehicle those are likely not Gaussian. So that's the second thing I say. Okay, what if it's fat-tailed? So that pushes things up as well for both warheads. What if the accuracy is degraded? So 90 meters is my baseline scenario, but there are a variety of ways that the accuracy can be degraded. So differences in trajectory can change the accuracy. Probably the most interesting one that I have thought of. Now, if somebody knows more about this, actually, this is something I read from a 2018 paper. It may be a little different now. So if somebody can help me out with this, that would be great. But my understanding is that the way the Navy corrects for weather is they send out a weather data set. They call it ballistic parameters. And it's a three-dimensional mesh over the target area, and each point in the mesh has a set of parameters that are corrections. Due to the fact that the submarines are underwater, they rely on extra low frequency or very low frequency, and that limits the amount of information that can be carried in these data sets. For a small target set, as in a testing scenario, or if you're fighting with North Korea, you can have a finer mesh, and that can enhance your accuracy. I would put money, if this formulation of the problem is the way that it's really done, I would bet money that the Navy tests with the more accurate data set. In a large target set, they have to send a coarser mesh. Now, the open source reading that I've done suggests that about 100 meters of error reduction are accounted for by this ballistic parameter, and the difference between some of the different course accuracy levels in the data set might account for about 30 meters. So that's why I say, okay, what if it's 120 meters? That's still exquisitely accurate. The Minuteman, that's the number for the Minuteman. Okay, so that pushes things up considerably as well. What about degraded reliability? This is where the STS literature on the politics of testing comes in. Now, there's been some recent failures with the Royal Navy. There have been considerably fewer failures with the US Navy. It's the same system. I'm not sure what the difference would be, but it's definitely the case that both navies have a strong political desire to demonstrate consistent testing. There are things that they are likely doing to the systems to make them safer in the test that might affect the performance. Also, when they test them, they launch 1, 2, maybe 3 missiles. In a real counterforce strike, they're going to have to launch all 24 of them in a short period of time. So once they launch the first one, they revealed their location. These are going to create additional possible failure modes that they may not know about before they do this. And then there's debate in the nuclear weapons community about how much we can rely on the numbers that the DOE publishes for, or that the DOE quotes for its reliability. Anyway, there's a variety of ways in which reliability can be degraded. Suppose that it is. So that really affects things for the W88, in part because one of the main failure modes for the W88 is outright system failure. And that's when the dust cloud actually becomes really important, because it's the second shot that it affects more. If I were to relax the assumption that the dust cloud doesn't affect the W76, that would probably be further up as well. What if China can have harder silos? They have massive surpluses in virtually all the materials that you use to harden silos. There's also questions about how we extrapolate PSI numbers up to extreme levels. So the data that we use is from tens, maybe 100 PSI, and we're extrapolating that up to really thousands of PSI. Harold Broad had a paper where he suggested that the limited data that we have, or we argued that the limited data that we have suggests that the standard scaling laws might over-predict the lethal radius by about 50%. This would be similar to a hardness change in hardness rating. So there's a variety of things that could lead to this. So that also affects things quite dramatically. The last part of this analysis that I did is I tweak each one of these parameters by a smaller amount, but it's a composite deviation from the baseline. Remember, previously, I'm only doing one thing at a time. It's not cumulative, but this one's cumulative. So 100 meters CEP, that's still a really accurate system. A little bit harder in the hardness rating, small degradation in reliability, so on and so forth. So now we're basically off the charts.
Wow.
And when I say off the charts, I'm again referring to this idea of a range of meaningful damage limitation. I think for almost any theory of damage limitation, the US is going to want to know where it sits in this range for this to be useful. But if these small changes in input parameters that the attacker really can't know with certainty lead to variations that span this entire range, I would say that complicates most theories of what the US stands to gain from, strategically speaking, from damage limitation capabilities. So I'm sorry I went a little bit over. That's the end of my talk. I didn't really dive into the mechanisms from the normal accidents theory. I'm happy to discuss that as well. But maybe I'll open it up for questions.
Wow, super interesting. Be back to the 70s. No, very, very interesting. As normal, we'll start with our fellows asking questions. And are any fellows interested in asking questions? For graduate students or fellows?
Okay, I can.
All right, Lindsay Rand, please go ahead.
Sorry, I've been like following you on your circuit now. Okay, so on the slide where you have your main graph, I guess, I first of all think this is amazing work, and I definitely think that this will really, really push the dialogue. I guess my main concern from looking at this would be that your pushback would be is there a chance you're biased in a unidirectional assumption, because you're assuming that complexity makes the trident systems worse. You're not considering ways in which they might perform better with some uncertainty, because uncertainty can cut both ways. And then conversely, aside from assuming that we might be underestimating PSI hardness of the ICBMs, you're not considering how complexity could make the ICBMs less resilient. So I guess how would you address that concern about bias?
Yeah. Should I respond?
Yes, please go ahead.
You're absolutely right. So it could be the case that the silos are less hard, right? It could be the case that the systems are more accurate, or that the attacker might luck out. I would say a core part of my theory is that the attacker is not going to want to count on that. The attacker needs to kind of know, and that the attacker won't be able to know that that's the case. So there are certainly ways that the attacker could luck out. I think that doesn't necessarily translate into a usable system, basically, because these small variations are resulting in large changes in potential human suffering inside the United States. So there are certainly ways things could have gotten better for the attacker. Now, in terms of deliberate improvement of the systems, there's a section in my article. This is where I draw from the Dick Garwin. So we could have more accurate systems. So that there's an argument that Dick Garwin made back in '76, where he said the defender doesn't have to count on the fratricide. The defender can just launch a loft, basically balls of metal, the kind of little balls of metal that you would buy for ballast if you are into boating, super cheap. Launch them into the air, and these would be enough to kill the reentry vehicle if they're in the path. Interestingly, with accuracy, the higher accuracy systems constrain the volume that the defender would need to fill with metal. There are also things you can do that I discussed to slow the descent, similar to the little wing that's on a maple seed to slow maple seed's descent. There are simple kind of low-tech things you could do to fill that space with metal that would get easier as the attacker systems got more accurate. I can't take credit for that argument because I basically lifted that out of Dick Garwin's old paper. I was fortunate enough to have some discussions with him before he passed about that topic. In terms of deliberate things that the attacker can do to improve their systems, part of my argument is that the defender can just do kind of simple things to shake the boat or shake up the scenario enough to disrupt those capabilities. I could be wrong in that, but that's basically my argument. That's why, that's why I'm here trying to get feedback. But I've certainly chosen to model things that illustrate things that could go wrong for the attacker. And I think the uncertainty there benefits the defender. And the defender is, I don't think the attacker is going to feel much better by saying, okay, we could luck out and they could just not have hardened their silos or something. So I guess that's my response to my choice of what things I'm modeling. In reality, I think it's worse for the attacker. There's things I'm not modeling. I'm not modeling the blast wave, not modeling the head of the mushroom cloud.
But on the defender side, if they're inferring their own complexity, then that could lead to the same amount of like apprehension, I guess, is my concern.
Well, so what happens if the defender loses all their weapons? That means they just didn't kill, they killed a few million less Americans. Doesn't mean that.
Yeah, that's good.
So it's like the cost, the connection between system performance and cost is for the attacker really acute. By the time that the defender has to launch its missiles, deterrence has failed. It's not going to save any, it's not doing counterforce, so it's not going to save any of its own civilians if its systems work better or less. So uncertainty isn't quite as acute for the defender. I don't know if that quite does it.
Okay, excellent. We'll throw the floor open. If those around the room have questions, you're welcome to raise your hand and indicate your interest in asking a question. We also have a very experienced group of listeners online too, so I invite our online participants to place your question in the chat, and I will call on you as the discussion develops. So anyone next? If not, let me just ask a question while you're thinking about, this is very complex work, and I really take my hat off to you, Christopher, for doing this work again. But why do you suspect, this is a broad-ranging question, this debate has obviously been going on since the 70s, and I want to again give full credit to people like Dick Garwin and also John Steinbrunner, who did a lot of very important work starting in the mid-70s up into the 1980s to point out these issues. And so why at the current moment is it your feeling that suddenly this counterforce debate has surged onto the scene with so much energy? And thank you very much for bringing these issues up again, but I'm kind of interested in your view as to why there's not been a kind of more vigorous debate on this, given this history that people remember. And again, I thank you for your work, but why is it that the counterforce debate has been so dominant, I guess, is the current...
or the counterforce, the sort of counterforce optimist.
The counterforce optimists. Why have they been so optimistic, given this history and given your work in the recent period? Why haven't there been more questions raised? I guess that's a simple way to ask the question.
Well, the short response would be they're starting to get raised. So Charles Glaser just published an edited volume in, I think it's Journal of Strategic Studies, that examines things. And, for instance, mobile missiles, searching for mobile missiles, that's another aspect that I'm not simulating. So a paper by T.D. McDonald simulates the search, the searching problem. And basically, I think, I don't want to put words into his mouth because he doesn't use my language, but I think he comes to a similar conclusion with the mobile missiles, that the defender can do pretty straightforward things to really complicate the searcher, or the seeker, I think he calls it. So I think some more recent literature from that kind of calls into question counterforce has recently been published. I think the Lieber and Press paper came out at a time where not a lot of people were thinking about strategic nuclear issues.
Mm-hmm.
We were more
That's
thinking
fair.
about things like nuclear proliferation. And so it was, and I critique that paper in mine, but I still think it was a useful paper because I wouldn't have gotten into this without reading that paper. I actually got this idea when I was having my students reproduce that calculation. So I think there's insights that can be gained from that calculation, even though I was critiquing it in the talk. I think there is also, when one is a young well, I don't know how young he was, but when at least in the postdoc phase, there was a cachet to like emerging technologies
Mhm.
and how they're changing like, so you can kind of, there's almost a template one can use for like what seems like an exciting project to say like, there's, we always thought it was this way, but with this particular emerging technology, it's fundamentally different. And after years of being in this field, you see that template move from topic to topic and technology to technology. And you can kind of interchange the technologies. And there's a little bit of a like public amnesia, I think, when the same type of argument comes around and we forgot that we've been doing this argument over and over again, right? So, and that's not to sort of diminish the importance of emerging technologies. One part of Lieber and Press's argument that I would embrace is that their target was the theory of the nuclear revolution, which says that no competition matters anyway. Doesn't matter if you'll never be able to do a first strike, and the defender doesn't really have to care, and it's really just domestic politics that drives arms races and right. And I think Lieber and Press, part of their argument was that, okay, if one side develops like really accurate missiles, the defender has to care about it. Like that part of their argument, I would say, is still intact, even if I'm right. Yeah, my intervention would be that the defender, what they have to do is it's not comparatively challenging from a technological standpoint. Sorry if that was a little long-winded, but
No, that's good. And actually, it jumps into the issue that Gonzalo Vergara is bringing up, which is please address the Golden Dome issue. I'm tempted to say after your presentation, why do we even worry about missile defense? We've got the dust to take care of the problem for us. But you want to address, talk about new technologies, modern defense technologies, missile defense technologies, and how they might in some way further affect this problem.
Absolutely. So this would, I think, probably the questioner is thinking if the attacker has a really effective missile defense system, they can deal with this. So you do the first strike, you get as many as you can, and maybe you do something like this, and then the remaining ones you can get with the Iron Dome or the Golden Dome. I have to be transparent in that I have not yet modeled that part of the problem. What I've tried to do here is pick what I think is the lowest hanging fruit for the counterforce optimist, which is counter silo attacks. Almost everybody thinks that the only function of silos is to just absorb a bunch of missiles. We'll get them all in the first strike. And my wager has been in this paper that if I'm right for the simple case for the counterforce optimist, much more complex cases like missile defense, searching for mobile missiles, searching for submarines, are going to be subject to this balance of nuclear humility in perhaps even more profound ways. However, to be fair, I have not modeled the missile defense yet. That's on the agenda. But depending on how this paper goes, I'll turn this into a book and I'll do that. One thing I'll say about what I can just speculate of how this will go. I think I will be impressed by the fact that Elon Musk and whoever has really lowered launch costs. So during the Cold War, one of the big technological barriers was that just the economics of the launch costs for space-based interceptors would have been a barrier, and that's probably mitigated now. That's the argument that I've heard. I think I'll be persuaded by that argument when I look at it. I think there will probably be other parts of the system that are going to create problems. And another thing that I'll say is that with the Iron Dome, so one of the things that you really gain from the STS literature that I didn't dive into as much is that the difference between prediction from testing and testing scenarios versus actuarial knowledge that you gain from real world applications and operation and failures that you didn't see coming and you make small adjustments. There's a book by John Downer called Rational Accidents that addresses that question with airplanes. And he suggests that it's just actuarial knowledge that allows us to make these systems more reliable. Probably with Iron Dome, they've used it and they have made tweaks to the system. They've learned along the way. The thing that distinguishes there's many things that distinguish Iron Dome from the Golden Dome. The speed of the thing for intercepting would be quite different. One of the things that distinguishes nuclear is that we can't really test these things, and we can't in a holistic way, and we can't accumulate operational data to learn about the unforeseen failure modes the way they can when we actually deploy systems in the field. So that's probably something that will, but having not modeled it, that's just my speculation at this point.
Okay, very good. Johanna, go ahead.
Yeah. Thanks for the talk, Chris. I don't really have a substantial question because I'm honestly convinced. I think my speculation is that we don't have a lot of questions in the room because this is so rigorous and convincing that I'm like, yeah, I don't really know why we're using the standard model. Like, that's all clear to me. And you explain it in a way that I followed like complex physical like phenomena that I didn't know I could follow. So that's cool. So my question is actually about asking you a little bit to speculate about like why we're clinging to like the standard linear model and what might be. So basically, because you couched it in this term of like techno-optimism, and if you could connect this to, in a way, the policy debate, like is there a benefit of being techno-optimist when it comes to nuclear strategy? Or is it not? Because obviously the way that you present it is that it would be pretty prudent to, calculate with the worst case scenario, which would be what you have shown us. So like, yeah, I'm basically asking you to speculate. Where do you think it comes from? And you alluded to it a little bit, that it's just kind of like a public, what did you call it? Public amnesia whenever it comes to, emerging technology. We've seen this with the airplane. We've seen this with nuclear weapons. We've seen this with AI. Every time it's like, this is going to change everything. And then it doesn't really change that much, right? And so what do you think are like the political reasons maybe for why, for example, adopting more complexity or chaos theory models might not be as attractive for nuclear strategy?
Yeah, so that dives into a bunch of things. And one of them I want to actually clarify from my talk. So I've written this paper to be agnostic about what the US Department of Defense does. I have to imagine they're doing much more sophisticated modeling than what I'm doing. I would be shocked if they were using the standard model. I think that model is useful for teaching purposes, and that's why they so I don't think so this was an intervention in the political science literature. I don't think the US government is necessarily doing this sort of thing. I'm also kind of trying to be agnostic about what China's really doing. But anyway, so that's a clear point of clarification. In terms of what drives, the question of like what drives arms races is as old as the arms race. I think it's a little bit beyond the scope of this project, so that I'll say that. But I think I err on the side of those who argue that there are things like bureaucratic politics, and then those can get entwined with, inter-service rivalry, and those things can get intertwined with the technologies themselves to kind of drive things toward the trajectory that technologies take. So Don McKenzie's work is what I would probably point to on that. If I were to look at, what's driving things, it's hard to study this stuff because it's classified. If I were to study this sort of thing, I would probably model that research off what Don McKenzie does, and my hunch is I would arrive at a similar result. So I can't really go beyond that in speculating like what drives. It's not just the standard linear model. It's the insane resources that we've dumped into accuracy and missile defense. Somewhere somebody must be committed to this sort of thing, but I'm not sure. I'm not sure that it really is driven by strategy. The Don McKenzie story is that strategy is an afterthought, and that it's things like inter-service rivalry and other things that drive technologies, and that it's after the fact that we say, oh, we of course made it for this reason. So that's kind of the direction I probably would look in if I were studying that actual question, which I can't right now.
All right, very good. Ori, go ahead. Ori Rabinowitz.
Thank you so much. My name is Ori Rabinowitz. I'm a visiting fellow here from Israel, and I was interested by your comment on the Iron Dome, and I think it could be very interesting from an empirical perspective, to examine open source data on how Arrow and THAAD and the system in general combined worked in April and in October because as opposed to testing data, which tested here, that was on the ground deployment. And I think that, and I don't think Iron Dome is relevant for the discussion, because Iron Dome shoots short-range rockets, and we're looking at long-range ballistic missiles. So the arrow is probably more relevant to the general discussion. But just touching back on Perils theory, which I also agree with you, I think it's instrumental to our field in general. What the Israelis kind of discovered, or maybe were more surprised to, was that once you intercept the missiles, the problem of dealing with the shrapnel is actually much more acute than just intercepting the missile, and it underlines the complexity of the problem you're dealing with. So do you have any thoughts about how you can maybe operationalize or look into that kind of data, or would it be even relevant for an experiment like that?
I think it would certainly be relevant. I'd have to think about how I would actually research it. I think one of the things that makes that system difficult to study is that all the people who know anything about either side of it have an interest in telling a certain story about it. I think the politics of that is like a politics of capability on both the Iranian side and the Israeli side. So like, I think it's hard to get a straight discussion about what's really happening, because everybody who knows what the truth is has a stake in the narrative. So that's, I mean, I think I think I would probably, so I'm not as well experienced in using the satellite imagery. I've mostly studied the people that use it. So I probably would consult with them, and would be a starting point for that. But I think it would definitely be challenging to get at what the truth is about what Israeli practitioners have learned, what the Iranians or other groups have learned as they're kind of probing the system. Sorry if that's a cop-out, but it would certainly be relevant to, I mean, I've often wanted to find a case where there's an open record of deployment and how did things perform based on what people thought, how they thought they would perform before they deployed it. That would be certainly relevant to my study. And there's probably other systems that I could do that with.
One anecdotal thing that comes to mind, I think that once Iron Dome was deployed, they actually got better results than they were expecting, which isn't something you'd usually expect for such systems.
So that harkens to Lindsay's question.
But again, it's impossible to verify and can be also propaganda.
Well,
I seem to remember a certain surprise when I was first visiting Israel and getting their briefings. They seemed surprised that it was actually working so well. Are there any other questions in the room? Yes, we have two more. So let's go first here. Yes.
Okay.
And please introduce yourself.
Oh, yeah. Hi. My name is Kartikash. Oh, do you want to go first?
I think you have a table mic.
Oh, I have a table mic. Sorry. Is it on? Yeah, it's on. Okay. Hi, Kartika Shashikumar from San Jose State. I have a question about dust. I feel like there was a lot of discussion of the effects of dust, and I'm wondering why you picked that. I'm convinced. I don't know a lot about the physical effects, but there's also heat and blast. And was there a reason why you chose to focus on the effects of dust? And I'm also thinking about how we seem to be, I'm skeptical, but we seem to be entering into an era of more launches, like civilian space. And so is there research now on hardening re-entry vehicles against the effects of heat, blast, and dust, and may that mitigate some of the problems that you were talking about?
If it's okay, Chris, hold that question. We have one more question. We're just about out of time. So why don't you go ahead and ask your question too? Please introduce yourself.
Hi, I'll make it quick. My name is Shreya Lad. I'm the research assistant to Scott Sagan. My question is about whether you've seen any evidence in China's changing conventional and nuclear buildup, but also its doctrine and posture that might indicate that China is also taking something like your theory of nuclear humility into account and trying to preserve its ability to stay, to use scrappy technologies to offset the U.S. advantage. Is there anything that might lead you to believe that this is the case?
I think I'll go backwards.
Okay.
So to answer that last question, so that would take there are vigorous debates among China specialists about exactly that question. And there's kind of two different sides that I can kind of detect. So one side I think would be like people like David Logan, trying to think of a few other names, for some reason they're eluding me, who suggest, I think, something along the lines of what you're saying, like that their strategy reflects kind of what I'm doing. There are others that would suggest, I think Tong Zhao would suggest that there's other things driving, political things driving their modernization that don't have as much to do with strategy. For me to weigh in on that would take me well outside of like my expertise, because I'm not a China scholar. So what I try to do is I try to be agnostic about that. And I say, okay, well, this is effectively what we can see them doing. And I present that to the China specialists, and they might have different interpretations of whether or not that reflects what they think China's doing. So I don't have a strong view on what China's actually doing. And I've tried to write, just like with the US side, I've tried to write my article to be agnostic about what China's really doing. But what they really think they're doing. They may actually be just doing a missile sponge thing. That's another thing they could do. So I don't really know a strong answer to that question. I'm told by some people that they think that China's very concerned about survivability. So if that's true, then these are some things they could be, what I see them doing seems to make sense. So why did I pick dust? So there's a bunch of things I'm not including that I think will make things worse for the attacker. Like you said, there's things like heat, the blast wave. The heat, depends on so the heat is certainly like in the fireball with the 2-on-1 and the second shot window. The speed with which the fireball rises, heat would be a component of both how fast it rises, and if it doesn't, that's why it would be lethal to the reentry vehicle. So there's aspects where I am taking into account heat, but there are all kinds of things that I'm not taking into account. I think I can confidently say that none of them are going to make things better for the attacker. They're all going to make things worse. So I've tried to pick a few things that are illustrative of the effect that I'm talking about. I forgot the second part of your question. It was really important.
Are we moving towards mitigation?
So yes, but I think a lot of that research happened at the beginning of the missile age. So reentry vehicles are hardened to things like radiation and temperature, the rigors of reentry. Often what happens when you try to improve those things and you put a lot of effort, there's the curve kind of goes like this.
Right.
It's a diminishing effects. I think a lot of the things they could do to protect things from heat, or the warhead from heat and radiation and other effects, they've already done at the beginning of the missile age, and there's less low-hanging fruit in that arena. However, I can't guarantee. I'm sure research for protecting warheads inside reentry vehicles is probably ongoing throughout the missile age. I have been told that when people in the DoD model these things, they try not to, or plan the strikes, they try not to fly them through the mushroom clouds at all. They try to avoid them. The limited glimpse that people have given me, they say, well, we try to avoid going through any part of the dust cloud for some of the reasons. Now, there's another thing that once a system is in place, there's path dependence where it's hard to change it. So there's things they could do. I saw a patent for like a tungsten reentry vehicle tip or something that would, but they haven't implemented that. And my hunch is that the reason is that when you change that, you shake up the apple cart, and there's all these other things that you have to redesign. So I don't think it will be quite as simple, but I have to imagine all this stuff is ongoing, and I can't guarantee that they haven't figured something out.
Very good. Well, we are out of time. Christopher, thank you for a fascinating presentation, and I agree with the comments super rigorous, really, really interesting, easy to understand. Thank you.